Well, hello everyone. Welcome to tutorial number 7 for the course CC457A. So in this tutorial, we are going to look at some examples and focus on different ways to solve examples in game theory. So the strategies that we want to use can be categorized into three sections or three topics or three strategies. We first have the dominant strategy. So it yields the best payoff for the player regardless of other players' strategies. This is our first solution to the problems. The second one is the iterated dominant strategy or dominated strategy. You can call them both. Call it both. So it means that there is another strategy that outperforms that performs at least as good regardless of other players' strategies. And finally, we will look at Nash equilibrium. So a strategy profile is Nash equilibrium if no player wants to unilaterally deviate to another strategy given other players' strategies, so the player is happy with its strategy. Or in other words, no player can gain by deviating alone, that is, by changing his or her strategy single-handedly. So let's look at the examples and solve them using these three strategies. The first example is the good old prisoner's dilemma. So we're going to use DS, dominated strategy, to see if we can solve this one, or if we can find an equilibrium. So let's find the dominant strategy for prisoner 1 or player 1. We can say the dominant strategy for player 1, we have two options, two moves, where to confess or deny. For confess, we have this one and this one. So -10 minus 1 equals -11. And for deny, we have -25 and -3, so -25 minus 3 yields -28. Because this value is higher, like -11 is higher than -28, we choose -11, like confess, as the dominant strategy for player 1. Now let's check it out for player 2. Dominant strategy for player 2. And again, for prisoner number 2, we have confess and we have deny. Let me use red for this one. So DS for P2, we have confess, we have deny. So for confess, we have these two values. -10 minus 1 equals -11. And for deny, we have these two values. -25 minus 3 equals -28. And confess is the dominant strategy here. So because both players have a dominant strategy here, we can actually express we we can express confess as the dominant strategy equilibrium. So because both players have a dominant strategy, we can express confess as the dominant strategy equilibrium. Let's solve this problem with the iterated dominance strategy. So for player number 2, or prisoner number 2, we can see that confess, actually deny here is completely dominated by confess. Five is completely dominated by confess, because confess is -10 and deny is -5. So in this case, we can completely forget about this column. Because for prisoner number 2, we can say that confess here actually it's not the only reason, because -10 is greater than -25 and -1 is actually greater than -3. So basically we can forget about the deny column and go on with the confess column. So -1, -10 and -1 completely dominates the deny column, -25 and -3. So I can add here -3 as well, and here -1. Therefore, for player 2, deny is completely dominated by confess. Then let's go and check it out for prisoner number 1. Now we have only one column. For P1, okay. For P1, we have these two values, -10 and -25. So we're not considering the other column. So we have confess and deny. And we can see that confess completely dominates deny, because confess is -10 and deny is -25. So confess with -10 dominates deny. Therefore, we can get rid of this one. And we are ended up with this one. -10 and -10. which is, or to be consistent, let's write this one with black. So -10 and -10, which is confess is the IDS equilibrium. Which is the same as for the dominant strategy equilibrium. Now let's move on to Nash equilibrium. Okay. So the best way to identify Nash equilibria of a game is to first identify all of the outcomes that are not Nash equilibrium. So we're left with some outcomes that we can say they must be now Nash equilibrium. Let's start from a cell. For example, start from this cell, -25 and 1. So prisoner 1 denies and prisoner 2 confesses. If we want to move right, we need to check this value and this value. We can see that -1 is actually greater than -3. So we cannot move to the right from this cell, from -25 and -1. Because when we're moving to the right, we're considering the decision for prisoner number 2, from confess to deny for prisoner number 2. While prisoner number 1 has its own decision as before, which is deny here. So when we want to move from this cell, to the right, we must consider the values for the second prisoner, so -1 and -3. Can we move from a lower value, from a higher value to a lower value? No. We only move in the direction of the lower value to the higher value. And -1 is greater than -3, so we cannot move to the right side. Now, if we want to move like upward, so that would be the decision for prisoner number 1, from deny for prisoner number 1 to confess for prisoner number 1. Here we need to consider this one. Can we move from -25 to -10? Yes. So you move upward. Can we move from -10, -10 to -1 and -25? So that will be, in this case, going from -10 to -25. No, we cannot do that. We can only move in this direction, and here we can only move in this direction, and here, so that for the two cells on the right, we can only move from -3 to, so it's actually the decision for the prisoner number 1, from confess to deny. So we need to consider -1 and -3. So we can only move upward. And because we have two arrows ending up in confess cell, we can say that our Nash equilibrium is actually confess. The same as IDS and DS. All right, let's move on to the second example. So for the second example, then again, we want to solve it using the dominated strategy. dominated strategy actually. So method. Bob either runs or stops. The same is true for Alice. So the first thing that we need to do is to find a dominated strategy for Bob, or let's call him P1, player number 1, and P2, player number 2. So DS for P1. Here we have two options, run and stop. So for run, Bob has 1 and -1. So 1 minus 1 equals 0. For stop, he has 2 and 2. So 2 plus 2 is 4. So this one is a dominated strategy for Bob. Now, what is a dominated strategy for Alice or player number 2? Then again, we have like that red. So dominated strategy for P2. We have run and we have stop. So for Alice, we have 1 and -1, 0 and -3 and 3, 0. So Alice has no dominant actually strategy. That's it. We can't go any further. Like we cannot find a like an equilibrium point or solution with dominant strategy, because one of the players has no dominant strategy. Now let us use IDS, iterated the dominance strategy. All right, so for player number 1, Bob, player number 2, Alice. So for player number 1, let's see which action dominates the other. We have 1 and -1 here, and we have 2 and 2 here. So we can say that, considering player 1, we can say that stop dominates run. Because we have 1 compared with 2 and -1 compared with 2. And in both cases, 2 is like greater than 1 and -1. So we can forget about this row. Now let's check for player number 2. Considering P2. Now considering P2, player number 2 has 3 and -1. So it's obvious that stop dominates run. We can get rid of this one. Stop dominates run. Why? Because 3 is greater than -1. And here, because 2 is greater than 1 and 2 is greater than -1. Therefore, IDS equilibrium is like stop. So let's compare this one with that one. So for player number 1, stop is the dominant strategy. As you can see here, stop is the dominant strategy for player number 1. But in this situation for player number 2, we could not find a dominant strategy. But using IDS method, we could find that stop is also the dominant strategy for player number 2, resulting this. Now let's use Nash equilibrium. Let's choose a cell. For example, let's say this one is P1, this one is P2. Run for P1 and stop for P2. So this cell. Let's begin from this cell. If you want to move downward, that will be the decision for player number 1, switching his action from run to stop. So is this doable? Yes, it's doable because we have -1 over here and we have 2 over here, and 2 is greater than -1. And if you want to move from this cell to the left side, that will be this change of decision for Alice, player number 2. Can we do that? Can we move from 3 to -1? No, we cannot do that because 3 is greater than -1, and we can only move this way to the right here. And I can say we actually kind of found this solution. So that will be stop. The same as IDS here. This one is our Nash equilibrium because we have 2 arrows pointing toward that cell. But what about this one? What about moving from the run stop to stop run? Can we do that? Actually, yes, we can do that because we're changing our decision from -3 from stop to run, which is -3 to 1. And can we move from 1 1 to 2 -1? Yes, we can do that because we're changing the decision with respect to Bob from 1 to 2. So we can do that. And we can see that all the arrows end up to the 2 3 cell. Stop, which is the Nash equilibrium for this example. All right, let's move on to the third example. Then again, we have the same procedure. So let's start with player number 1. Player number 1 has 4 actions, A, B, C, D, and player number 2 has 2 actions, X and Y. First method is the dominant strategy. So let's find the dominant strategies for both players. For player number 1, A, B, C. So for A, we have 5 and 4. So 5 plus 4 equals 9. For B, we have 3 and 3. 3 plus 3 equals 6. 2, 4, and 2 plus 4 equals 6 again. 4 and 5. 4 plus 5 is 9. So we cannot find a dominant strategy because we have two actions that are that have the same value, so that have the same payoff, so we cannot choose between either of them. We need to actually change this strategy. But before that, let's go and do it for player number 2. For player number 2, we have two actions, X and Y. And see whether player number 2 has any dominant strategies. So for X, we have 2, 1, 1, and 3. The summation of payoffs. That would be 7. And for Y, we have 2, 2, 1, 4. That would be 9. So Y is actually the dominant strategy for player number 2. While player number 1 has no dominant strategies. Let's solve the problem using iterated dominance strategy. Let's go with player number 2. So we can also use this one. So we can see that here, actually action Y dominates action X. So looking at this table, we can see that 2 and 2 are equal. 2 actually dominates 1, and 1 and 1 are equal, and 4 actually dominates 3. So overall, we can say that the right column dominates the left one. So we can get rid of this one. Now we only have one column and 4 actions for player number 1. So for player number 1, which action can we choose? For player number 1, we can see that the action with the most payoff is D, because 5 is greater than 4 and 3. Therefore, this is our equilibrium point. Now let's use Nash equilibrium. Let's start from the farthest cell from the solution. So we actually kind of know that the 5, 4 is the solution, is the equilibrium point, Nash equilibrium. Let's start from 5, 2. All right, can player 2 change his or her action from X to Y? Actually, he can. So, and it's a like two-way arrow, because we have 2 on this side and 2 on the other side. And for this one, if player B is if player 1 is playing B, can player 2 change his or her action from X to Y? No, but can change from Y to X because 2 is greater than 1. Here we have 2 ways, and here we only have this way. Now, for this cell, let's say that player 2 is playing X. Can player 1 change his or her action from A to B? No, but can actually change the action from B to A because 5 is greater than 3. So this is also true for this one. And for this one, we have this way. Now, considering that player 2 is playing Y, we can have this one, or this one, and this one. So we can see we have actually 2 arrows ending up in this one, 5, 4 cell. So this is the Nash equilibrium, and actually 2 arrows end up in this one. This one is also a Nash equilibrium, but one of the arrows is like a two-way arrow. So the thing that we can say is that actually I realized I made a mistake here. Let me first correct that one. Supposed to be like this. Yes. Okay. So as I was saying, so this one has like 2 arrows, but one of them is a two-way arrow. So this is a Vic Nash equilibrium, while this one is a strict Nash equilibrium. Strict. Okay. Moving on to the next example, the last example, like before, starting with DS. Player number 1 has 3 actions, U, M, D, and player number 2 has 3 actions as well, L, C, R. So let's find the dominant strategy for player number 1. They have 3 actions, U, M, and D. So for U, we have 1, 3, and 40. That will be a total of 44. For M, we have 10, 50, and 6. That will be a total of 66. For D, we have 2, 4, and 10. That will be 16. So obviously, M is the dominant strategy for player number 1. Now, dominant strategy for... I was doing that. Sorry. Red. Dominant strategy for player number 2. We have 3 actions, L, C, and R. 10, 10 and 20 and 20. That will be 50. And here we have 50 as well. And here we have 0. Oops, sorry. So we can see that P2 has no dominant strategy. I didn't clear away. So P2 has no dominant strategy. Let's use IDS. See which one is the equilibrium point or equilibrium strategy. Starting with player number 1, maybe. It doesn't matter from which player or from which cell or column or row you begin, you will end up with the same solution. Let's check. We can see that here, for example, for player number 1, comparing this with this, and maybe this and this. What we can say is that it's not a good choice. It's not a good choice. We cannot say that which one well, obviously we can say that M dominates the other rows, but we cannot be sure or say certainly with complete certainty. Because here 40 dominates 6 and 10 dominates 6 as well, and 40 dominates 10 as well. So let's start with player number 2. So starting with player number 2, we want to see which action dominates the other. So it's completely obvious that L dominates R, because R is 0, 0, 0, and L is 10, 20, and 20. Now, we cannot say that L dominates C, because we have a 20 over here and a 40 over here, but a 10 and negative 10 over here. So what we can say is that, so a 20 over here, a 10 over here, a 40 over here, a 20 over here, but a negative 10 and a 20 over here. So we cannot say that L dominates C. Now let's look at player 1. With player 1, because the last column is deleted, we can say that M with 10 and 50 completely dominates D and U with 1 and 3 and 2 and 4. So 10 dominates 1, 10 dominates 2, 50 dominates 4, and 50 dominates 3. So we can get rid of this row and this row, and we only have this 10, 20, and 50, negative 10, CLM. Okay. So we have only one action for M. We need to consider actions for L and C, which means comparing this value with this value. Well, obviously 20 is greater than negative 10, so this one is the equilibrium, meaning that ML is the IDS equilibrium. So here we found out that M is the dominant strategy for player number 1. So we have M over here, but we were hesitant between L and C, and and we actually found that L is the action to go with here, using iterated dominance strategy or dominated strategy method. Last example, last strategy, Nash. So with Nash, let's see. Let's start from this one. Can we move upward, like changing the decision from D to M? No, we can't, but we can move downward actually from M to D. Can we move to the left, changing the decision of player 2 from R to C? We actually can, because of 40 and 0. 40 is greater than 0. Can we change the decision for player number 1 from D to M? Yes, we can. From 4 to 50. Can we change the decision of player number 2 from C to L? So for C is 40 and for L it's 20. Actually, no, we can't. Okay, I will just write down the arrows. So for this one, it's 50 actually. This one moves to, yes, all right. And this one from 0 to 20. This one from 10 to 20. And the other one from 1 to 10, yes. And this one from 2 to 10, yes. This one from 6 to 40, yes. And this one from 3 to 50. And I think that's all. So we can see we have 3 arrows ending up in this one, which is ML. And this is our Nash equilibrium, which is the same as what we found with IDS. So that's actually about it. That concludes the tutorial number 7. And these are also the references that you can go to and look at other examples and other ways of solving the problems. Actually, I got the examples from these references. You can look at them for more examples if you want. And that's about it. Until next time.